unravel one of the coolest, most mind-bending mysteries in all of physics: how electricity actually flows through our world. You know, we use it every single day, right? We flip a switch, we expect immediate results, but the physical reality of what is actually happening inside those wires? It is absolutely wild. Today, we're going on a journey alongside the electron, zooming from the massive, untamed power of nature all the way down to the incredibly precise, microscopic control required for the very device you're using right now. When we think of electricity out in the wild, we usually picture the sheer scale of a lightning strike. A typical strike carries tens of thousands of amperes of current. But here's the thing. This is a prime example of a non-steady flow of charge. It's just a sudden, chaotic, massive discharge from the clouds, straight down through the atmosphere to the Earth. The sheer magnitude of this unguided energy is almost impossible to wrap your head around, and as we know, it can definitely bring disastrous results. But in stunning contrast, check out this number. This represents microamperes, literally 1/1,000,000th of a single ampere. At the complete opposite end of the extreme, the electric currents flowing through your own human nerves right this second, keeping you alive and functioning, are measured in these tiny microamperes. They're incredibly small, completely steady, and perfectly controlled by your biology. It really puts into perspective just how unimaginably vast the spectrum of electrical current actually is. So, here's our roadmap for today. We'll start with extreme currents and steady flows, look at Ohm's law and resistance, take a trip inside the conductor, tackle the great electron paradox, and finish up with what happens when Ohm's law fails. Let's kick things off with Section 1, Extreme Currents and Steady Flows, moving from chaos to control. This brings us to the fundamental difference between those wild atmospheric charges and the electricity we actually use in our daily lives. Lightning is what physicists call a transient flow. It happens all at once, bam, and then it stops. But to power something like a flashlight or a battery-driven clock, we need a steady flow. Think of water flowing smoothly and continuously down a river. That is exactly how we need electrical charge to behave. The whole goal of electrical engineering, really, is transforming that chaotic potential of nature into a smooth, predictable, river-like current that we can actually rely on. Which leads us perfectly into Section 2, Ohm's law and resistance. Basically, the physical hurdle discovered way back in 1828 by George Simon Ohm. The crucial takeaway here is Ohm's law. This beautifully simple equation tells us that voltage, which you can kind of think of as the pressure pushing the electricity, is equal to the resistance of the material multiplied by the current that flows through it. So if you want a specific current to flow, you absolutely have to apply enough voltage to overcome whatever physical resistance the material naturally has. And resistance isn't just some abstract math equation. It's a very real physical hurdle. Let's go back to our river analogy for a second. If you have a conductor, say in the shape of a rectangular slab, and you put two of those slabs end to end, you've just doubled the length of the wire. Well, according to Ohm's law, you've exactly doubled the resistance. It's a journey that is twice as long. On the flip side, if you cut that slab in half, lengthwise, effectively halving the cross-sectional area, you also double the resistance because the path is now half as wide. The physical dimensions of the conductor directly dictate the flow. Let's dive deeper for Section 3. Inside the conductor. Get ready for the bumper car chaos. If we zoom all the way down, bulk matter inside a metallic conductor is astonishingly dense. Just a single gram of water has roughly 10 to the 22nd power molecules. Solid metals are incredibly tightly packed. And inside this ultra-dense metal, some negatively charged electrons are free to move. Because of normal thermal energy, these electrons are zipping around, but it is utter chaos in there. It's literally like a microscopic bumper car arena. These free electrons are constantly crashing into heavy, fixed positive ions. They bounce off, completely changing direction randomly after every single collision. Because they're bouncing around in completely random directions, if you were to average out all their movements, they actually go absolutely nowhere. There's zero net flow. But there is a tiny, tiny window of time between these collisions, which physicists call the relaxation time. During this microscopic fraction of a second, the electron is briefly traveling in a straight line before it smashes into the very next ion. And that brings us to the climax of this explainer in Section 4, the great electron paradox, the snail versus the light. Okay, so here is the paradox. When we apply an electric field using a battery, those chaotic bouncing electrons get a slight push. They're still bouncing around randomly, but they start to slowly drift in one overall direction.
But here's the kicker. Based on the physics of a standard copper wire carrying a typical current of 1.5 amperes, that drift speed is only about 1.1 millimeters per second. That is practically a snail's pace. It would literally take a single electron hours to travel a few meters down a wire. So how on earth does a light bulb turn on the exact millisecond you flip the switch?
The answer is totally mind-bending. While the physical electrons themselves are barely crawling down the wire, the electric field itself travels through the conductor at the speed of light. That's roughly 300 million meters per second. So establishing a current doesn't mean we're sitting around waiting for one specific electron to travel all the way from the switch to the bulb. Instead, that electric field instantly ripples through the entire circuit, pushing all of the tightly packed electrons everywhere in the wire at the exact same time. The local electrons right next to the light bulb, they start drifting immediately.
And this actually solves another massive piece of the puzzle. If they are moving so incredibly slowly, how are they delivering so much power to our appliances? The secret here is enormous density. There are an unfathomable 10 to the 29th power of free electrons in just 1 cubic meter of conductor. That's a 10 with 29 zeros. So even though a single electron's drift speed is incredibly slow, when 10 to the 29th of them all start drifting in the exact same direction simultaneously, it results in a massive, powerful current. Finally, we arrive at section 5, when Ohm's law fails. The modern twist.
Ohm said voltage is always proportional to current, but in reality, there are 3 distinct ways this famous law completely breaks down. First, some materials are simply nonlinear. That clean proportion just stops working entirely. Then you have things like diodes, which are sign-dependent. That means if you reverse the direction of the voltage, you get a totally different amount of current. And then you have bizarre materials like gallium arsenide, which are non-unique. This means you can actually have multiple different voltage values that give you the exact same current, total rule breakers.
For a long time, you might have thought these were just annoying errors or glitches in physics. But these failures aren't mistakes. As our source material points out, these rule-breaking behaviors are actually widely used and entirely intentional in modern engineering. We absolutely rely on them. So ask yourself this. Isn't it incredible that the entire digital world, your smartphones, your computers, the very device you're using to watch this explainer right now, is only possible because we learned how to master semiconductors, materials that stubbornly refuse to follow the oldest rule in the electrical book? By harnessing the materials that break Ohm's law, we moved from simple light bulbs to complex computers. So if breaking the oldest rule in the book unlocked the entire digital age, what other laws of physics are we going to have to break to build the technology of tomorrow?